Hi and welcome to this section where I would like to wrap up our study of the difference operators. So we would like to define what we call the average operator. Okay, it is denoted by the symbol mu, and then the average operator mu is defined as the average operator of f at x is going to be defined as 1/2, okay, multiplied by f of x plus h over 2, then plus f of x minus h over 2. Okay, we'll just leave it at that. And then we would also like to define a differential operator. We represent by the symbol capital D. Okay, so the differential operator has the following property. The differential operator of f at x is defined as the derivative with respect to x of f of x, and we can denote it by f prime of x. And then the second differential operator of f at x is defined as the second derivative of f of x with respect to x, and we can write it as f prime prime of x. Okay, now we would like to look at the relations between the operators. Some, of course, we cannot complete everything, but okay, in particular, I take us to look at the relation between the operators in terms of the shift operator E. Okay, so remember we looked at the forward difference, we looked at the backward difference, we looked at the central difference, we have seen the definition of the average difference, and then or the average operator, and then we also have the differential operator. Okay, so we are going to write a series of results here, but most of them simply follow from the definitions. Alright, let's go. 1. We know by definition that the forward difference operator of f at x is going to be f of x plus h minus f of x, okay, which we know in terms of the shift operator. This is the shift operator of f at x, okay, then minus f of x. So we know that we can write it as this is a minus 1 times f of x, okay, and therefore we can therefore say that the the forward difference operator here is equal to the shift operator minus 1. By definition, we know that the backward difference operator of f at x is going to be f of x minus minus f of x minus h, which is f of x, and then we know this is the definition of the inverse shift. Okay, so we know that we can write this as 1 minus the inverse shift times f of x, okay, and then we can say that the backward difference is going to be 1 minus the inverse shift. We can further simplify this and then say it is 1 minus 1 out of e, and then which is going to be equal to e minus 1 over e. 3. The central difference operator of f at x by definition is f of x plus h over 2 minus f of x minus h over 2. So by definition we see that this is the shift to the power half of f of x. Not so, because it is the value at the next point. If it was shift operator at f of x, it would be the value of f at the next point, which would be x plus h. But since here we are just having power half, then it is the value at the next node, which is simply x plus h over 2. So we have that, and then minus, then no prizes for guessing, that this is simply that. And then the usual way we have done, the same way we have done the rest, we can come up with now e to the half minus e to the power negative half. How about if we have the average operator here? By definition, we said it is that, then f of x plus h over 2 plus f of x minus h over 2. Okay, and then this is 1/2, and then by definition we know that this is going to be e 1/2, okay, of f at x, and then this is going to be e minus 1/2 of f at x. So what do we get here? So we shall come up with now, okay, we can deduce that now that's the average operator is going to be given by that 1/2 plus e minus 1/2. Okay, what else is there? Okay, okay, we would like to deduce also a result here. We know, maybe we can call this is 4, so we can call this 5. The shift operator of the shift operator okay, on f at x is f of x plus h. Then we can expand this using a Taylor series expansion. Now if we expand that using a Taylor series expansion, we can write that that is going to be equal to, by a Taylor series expansion, okay, we have f of x, this is over 1 factorial, plus this is the first derivative, okay, plus h squared over 2 factorial times the second derivative of f, plus h cubed over 3 factorial, third derivative of f. I am writing this on the assumption that we know how to get these Taylor series expansions. These were taught in high school. If you're not sure, you can maybe just Google Taylor series expansion and then you'll see a simple result. Okay, so we can write this as f of x plus, this is h over 1 factorial, but we know this, we said that that is the difference operator, okay, not the difference, the differential operator, okay, of f at x. Similarly, this is going to be h squared over 2 factorial, then the second differential operator of f at x, plus this will be h cubed over 3 factorial, the third difference operator of f at x, and so on and so on. Now we can just pull out f of x, and then we can write this as 1 plus hd, then plus h squared over 2 factorial d squared plus h cubed over 3 factorial d cubed, plus and so on and so on, and then we have f of x. Okay, so on this side, remember we had, this is the shift operator of f at x. So we can see, okay, now I would like you to see that this is just the expansion of okay, maybe before we go to that, I would like to remind you, just as a side note here, you know the expansion of e to the x, okay? You can also check it out if you're not so sure, but you know that the expansion of e to the x is just that over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on and so on, okay? Which I think we can write as the summation from I equals to 1 up to infinity, maybe let us use n, of what? Of x to the power n over n factorial. Is it equal to 1? No, not from 1, from 0. Because when n is 0, 0 factorial is 1, and then x to the power 0 is 1. We have the first term. Then when x is 1, we have x over 1 factorial. When x is 2, yes. So, yeah, we can write it is that form. But this is not the point. The point is actually here. I would like you to relate this to that. So we see that whatever we have in here, if we compare with the expansion of e to the x, that we can simply write this as e to the hd, the expansion of e hd. In other words, wherever there is x, you're simply going to replace it with hd. This is hd squared, this is hd cubed, and so on and so on, okay? And what do we have this side? This side we had this, okay, and then times that. So you can easily see from here that we are going to get that the shift operator is equal to exponent hd, okay? And then we can take maybe the logarithms on both sides, for which we can have that hd will equal to log of e, okay? And so that is the relationship which we can deduce. So there are many relationships, we cannot exhaust all of them, okay? Just try to practice a few more and see if you can really derive what is in the notes. If there is anything you don't understand, you can always put in the comment section. So thank you, and see you in the next video.